What we are going to do today is transition from the differential rate law into the so-called integrated rate law. For the integrated rate law, we only discuss the single reactant case. Zeroth order is actually rate equals to K. First order is rate equals to K times your reactant to the first power. Here I use A represent our reactant. For the second order one is actually rate is equals to K times A to the second power. This is what we write for the differential rate law. You need to go from here to here. One new prime actually shows up, which is actually your time. So whenever you see a question talking about the time, that means you are going to use the integrated rate law to solve the problem. And then here we only talk about zeroth order, first order, second order. That's pretty much all the orders you're going to encounter for this chapter. And then if you look at this equation, no matter it's zero, first, or second orders, in all equations only contains 4 parameters, which is actually your initial concentration highlight as A naught or A0. That means actually initial concentration of your reactant species A. And then the other thing is the concentration of A at a certain time point T. And the third one is your rate constant K. And the fourth one is the time. In your question, you always get 3 and solve the fourth one. For this chapter, one thing that you're going to encounter the most will be the first order one. Okay, so make sure you nail down the first order derivations. So in order to actually go from the differential law to the integrated rate law, there are a few math equations that you need to get really familiar with, which I highlight here. This one is for the zeroth order. That is actually for your first order. That is for your second order. So for the first order, we know when you write out the rate, so the disappearing rate of your reactant can be written as the change of your A concentration over time. Because it's disappearing rate, so you need to put a negative sign in the front. So this is actually how you define the rate. And then we know for zeroth order, it just equals to your K. The next thing you do is you multiply dt on both sides. Then you have dA is equals to K dt, and you move the negative sign to the right. Do the integration on both sides, okay? And that's the time we are going to use math equation number 1. So what it says is actually if you have dx, you do the integration of that, you will convert back to x. From there, we know there are things once you do the integrations, you actually get back to here. What this means is actually equivalent to this. That means actually I want to do the calculate the difference between your A between time t and time 0. And then for this part, then it's just equivalent to this. So t change from t to t0. K is a constant, so it remains the same. Rearrange all the terms, then you get to this first equation. AT is going to equal to A naught minus K times T. Okay, so this is the equation that you need to memorize it. For zeroth order reactions, the concentration of A at any given time T is going to equals to your initial concentration minus rate constant K times T. You can do the same thing for your first order and second order. So again, you start from with this. That is actually your rate on the left. On the right is actually K times A to the first power. Then you do the same thing, move your dt to the right, you do the integration and use your mathematical equations. Then you're going to get this equation for your second order reaction. Natural log A T equals natural log A naught minus K times T. For your second order is actually, again, on the left is your rate. On the right is K times A to the second power. And then again, move your dt to the right, integration on both sides. Then use the equation number 3. You can get to this final conclusion. 1 over AT is going to equals to 1 over A naught plus KT. Then memorize this. Make sure you have a good memory to connect this, and that. Because these 3 equations are all the equations you need for the integrated rate law for this chapter. And then what can you actually learn from this equation is that Assuming today you put your AT as Y, my T is X, this is C. If you plot out your Y versus X, which means if you plot out your AT versus time, it will look something like this, where at time 0, that's giving you A naught, and the slope of the line is going to equals to negative K. For your first order, I also make the x-axis as T, and my y-axis, if I plot out natural log AT, is also a straight line. But at time t, you're going to get natural log A naught. Again, the slope is going to equals to negative K. Okay, in third case, for your second order, my x-axis is T again. My y-axis is actually 1 over AT. So this will be your y, right? Equals to K times your x plus a constant C. It's again a linear relationship. So what you're going to expect is something that's increasing. The reason is because it's positive KT, right? So you know the slope is going to give you K. So this slide summarizes all the things we just discussed. Okay, the only thing we haven't mentioned is actually the half-life, which we are going to mention this, okay, when we give you examples. I think that's easier for you to actually comprehend the concept. Let's get started from the first question. Consider reaction AA Lefong's product, where the A naught is 5.0 m and K is 1 times 10 to the negative 2. Calculate A after 30 seconds. Assume the reaction is actually zeroth order, first order, and the second order. When you read these questions, what are the keywords? Time, right? This you will tell you to use the integrated red law. Then we come to these 3 equations that you need to memorize. This, and this. So depending on the order they provide in the question, then you know which equation that you should use, right? So let's start from the first one, zeroth order. So the equation you need to use is this. Let me write here. We know your A at any given time t is going to equals to negative kt plus your A naught. If you look through this equation and then you read through your question again, A naught is actually 5.0, right? That means this guy is 5. K is 1.0 times 10 to the negative 2. What's the time you need? 30 seconds have passed, right? That means actually 30 seconds after, right? So you know your T is 30. So apparently this is a question that give you the A naught, give you K, give you T to calculate your AT, right? Go from the question to the equation that you need to use is the key to solve this problem. So you should train yourself. So like once you see this time information, integrated red law, find out the order, write down the equation, plug in the number, solve for the answer. That's how you should do it. For the first order and second order, you just need to switch to different equations and then plug in the numbers and calculate your AT. Let's go through the next question. This slide is going to tell you how to use integrated red law to determine the reactant concentration and the reaction time. Let's start from here. For a reaction where it shows the N2O5 is going to decompose to form the NO2 plus O2. The red law is this, where the rate constant K is this at 65 degrees C. And then it asks you, assuming the initial concentration is this, what is the concentration for N2O5 after 600 seconds? 600 seconds is the keyword because that information tells you this has to be related to the integrated red law. Okay, what is the reaction order? Does this tell you the reaction order? First, right? So when we say the reaction rate is equals to rate constant K, if it's zeroth order, it's actually to the reactant to the zeroth power, right? That equals to just K. So if you see R equals to K, that means it's zeroth order. But if the R equals to K times reactant to the first power, that's first order. If actually it's rate equals to k times reactant to the seconds power, that's seconds order. So from here, okay, even though it did not say, it did not tell you, from the equation you should know that this is first order reaction. Unit of k is another places that you can actually know what the reaction order is. Okay, so these are the three keywords that you should actually know. So since right now it's actually first order, you need to write these things out first. Okay, natural log AT is going to equals to negative KT plus natural log A naught. This apparently is the things you want to solve. Do you have K? 5.2 times 10 to the negative third per second. What's the T? 600 seconds. Plus natural log A naught, the initial concentration, right? So you know this is 0.04. Once you get these numbers, don't forget the things you have is actually natural log AT, right? So in order to convert the natural log AT to AT, you need to do the exponential on both sides. So you need to do the exponential negative 5.2 times 10 to the negative third multiply 600 plus natural log 0.04. Then you should be able to get the answer of 0.0018 m. So once you have those concepts, solving the second one becomes very easy. So assuming the initial concentration of this is 20 m, that means actually your A naught right now is actually 20 m. How long does it take? It actually tells you need to calculate your T. When you reach the concentration of 2n, that means actually your A at that time T is going to equals to 2. Again, use the same equation. Natural log AT equals to minus K times T plus natural log A naught. Plug this in to here, you got natural log 2. Going to equals to minus K. K is 5.2 times 10 to the negative 3. Multiply T plus natural log A naught is 20. You just use this equation to solve for your T. The T is going to equal to 442.8 seconds. Another type of question you're going to encounter a lot. Let's look at this one first. If a rate constant of decomposition of N2O5 at certain temperature is certain number, please calculate the time needed for the concentration N2O5 fall to 1/2, 15%, or 1/9. It's actually very similar to the things we see before. The only thing that changed is that it did not directly tell you the concentration of your AT. Rather, it actually describes your AT relatively to your initial concentration. When you say it's actually when the concentration of this drop to 1/2, that means your N2O5 at time T is going to equals to 1/2 of N2O5 at time 0. So in the second case, you need to decipher this as that your N2O5 at time T is going to equals to 0.15 times your N2O5 at time 0. And the third one is your N2O5 at time T is equals to just 1/9 of N2O5 at time 0. So once you have this concept, and we know this reaction is first order, right? So previous we say for the first order one is actually natural log AT is going to equal to negative KT plus natural log A naught. Therefore, I can move these things to the left. So it's going to become natural log AT minus natural log A naught. And this turns, you can put it all into a single natural log. Then it will be this on the top, that is actually at the bottom. Then it's going to equal to just your negative KT. You can actually move the K to the left. So you're going to get T is equal to 1 over K, negative sign, natural log AT over A naught. Put the negative sign into my natural log. It's going to flip this two, so that A naught right now is actually at the top, AT is actually at the bottom. So this is something that you might want to actually memorize. So once you have this, Then for the 1/2 condition, your AT is equal to 1/2 of the initial concentration. You can just replace this one as 1/2 of the A naught. And then the A naught is going to cancel out. And this natural log term becomes just natural log 2. So you know, in the end, the T half is actually equal to 1 over K times your natural log 2. If I give you the K, then you know what the time is. The reason I put 1/2 here is simply because this actually represents the concentration of A decreased to the half of the original concentration. So once you have this concept in mind, you can actually solve this one relatively easily, right? For the second part, we say the AT becomes 0.15 of the original concentration, right? So what it means is actually you can still use this, right? T is going to equal to 1 over K. A naught on the top, bottom will be 0.15 times your A naught. And then your A naught cancels out. In the question, you got the K, right? Therefore, you can solve for the T. And then this T will be T 0.15. So for the 1/9 it's the same, right? So your T 1/9 will equal to 1 over K. A naught, 1/9 of your A naught. And A naught cancels out. Then you can actually put in your K, then solve for your T. The key thing here is actually this is something that you also want to memorize. So the very last thing I want to go through is this. This is actually another type of question you're going to encounter, which is relevant to the plot we made in the very beginning. So in the questions, okay, you will see a lot of descriptions. But the key is actually you're always going to see a table that associated with that question. It gives you the concentration of your reactants at different time. It gives you natural log of the concentration at different time. And it's going to ask you what is the reaction order. So what you need to do is just need to plot out the concentration of your reactants or the natural log of your concentration over time and see which one gives you the linear plot. And that one will be the orders that you're actually looking for. Just to refresh your memory, if it is zeroth order reactions, if you plot out your concentration of your reactant over time, then you're going to get a straight line. In the questions, all you have is actually just concentration versus time or natural log concentration over time, right? So what you do is actually you just use your Excel to plot out these two things, whether Y is either this one or that one, and see which one gives you the linear relationship. The one that gives you the linear relationship is actually the reaction order for that specific reaction. One tricky thing of this thing is that when they describe the AT, okay, the concentration of your reactant at time t, it could be tricky. In your homework, be very careful about the wording. Sometimes they will say how many of the A remains and how many of A consumed. This actually describes the opposite thing. How many A remains is equivalent to the A at time t. That means actually the A concentration at a given time. How many of A consumed? Originally you have A naught. Right now you have AT. That's how many of A has been consumed.